This is our second chapter on waves and vibrations, and this is all about sound and how we hear. We'll learn a number of different concepts related to sound. So I will jump through several different ideas in this chapter. It's quite a long chapter. Okay. Here we see we have a tube with some air in it, and in that air, sound is going through to the right. Okay. So you can see sets of compression and rarefaction. You should see bands moving to the right. Where you see the band, that's the compression, and in between the bands, there is rarefaction. So the density is not uniform. We have effectively a density wave or a pressure wave moving to the right. I've highlighted for you 3 red dots, which are exactly like any of the other black particles, but just so that you're able to identify one of them. I want you to follow any one of them. They're all doing the same thing, and they're doing the same thing as the black ones. Okay? The red dots you will find are the particles of the air which are helping to move the wave forward, but they are executing simple harmonic motion in the horizontal direction. Yeah, so I want you to just notice that moves to the right, moves to the left, comes back to center. I'm looking at the middle one. Okay, so what kind of wave is a sound wave? Is it transverse or longitudinal? They're longitudinal waves, right? Okay. So this is the actual wave pattern. Okay. We learned that longitudinal and transverse waves are types of mechanical waves, and all mechanical waves need a source for the sound. So source for the disturbance or vibration. In the case of sound, I can hit the desk here. In the picture in front, you saw them percussing some drum, some kind of drum-like object, etc. Okay, so you need some source which produces that vibration, which is the sound, which then needs to move through a medium. So we need a medium such as air. So if you have vacuum and you have a source which is vibrating, you will not hear the sound. Okay, there's no sound produced because it cannot travel. There's no medium in which the disturbance can travel. So those longitudinal waves require that medium. Okay, here's the simplest thing that can produce a sound, a very pure tone. You will use this. This is a tuning fork. They come at several different frequencies, and usually the frequency is written here, like 512 hertz, 1000 hertz, and so on. Okay. So you take a mallet and you hit one side. Say we hit this side, then this side begins to vibrate. Yeah. When it moves out to the right, it compresses the air just in front of it. Yeah. And that's this compression after some time. So a higher density region is produced, which is the compression. As the time moves back, so time is this arm of it, as it moves back from its stretch, it now produces a rarefaction, and you can see that in the different colors here. The darker color is higher density, this is lower density. So we have our compression, we have our rarefaction. And then as it moves back out, you're going to get the next compression, and so on. So you have a whole set of compression, rarefaction, and if you plot these in a 2-dimensional graph, you're effectively plotting the density pattern. Yeah? How density varies with space. So this is a density wave or a pressure wave. Some of this we talked about earlier in the previous chapter. Yeah? Remember, the upper part is called the peak or the crest, and it corresponds to the compression. The trough or the lower part corresponds to the rarefaction. Okay, so certain categories about sound waves. Audible waves, which are audible to us, we're always talking in terms of human beings, okay? So we can hear frequencies that lie in the range of 20 hertz to 20,000 hertz, okay? So something below 20 hertz is inaudible to us. Something above 20,000 hertz is inaudible to us. But within that range, we need a certain volume, a certain intensity for the sound before we begin to hear it, and that sound we call 0 decibels. dB stands for decibels. We'll see later on what a decibel is. And we can hear to comfortably up to 120 decibels. So this is the range roughly in which human beings find it comfortable. If it gets any louder than this, your ear will start hurting. So those are audible waves. Then we have infrasonic waves. Infra means lower. Sonic has to do with sound. Infrasonic means lower than 20 hertz, okay? Where the frequency is lower than 20 hertz. And that means the wavelength is large, okay? And we have very large wavelength waves, for example, the earthquake associated waves, yeah? Seismic waves. So some animals are sensitive to these waves, for example, elephants and certain other animals too. They can figure out when the earthquake is coming much earlier than a human being can, yeah? And they try to move out of the area. So it's crucial to know that when we say audible, we're talking about the human range. The other side, higher than 20,000 hertz, are the ultrasonic waves, okay? So these are very high frequency, and these are audible, for example, to dogs, also to dolphins, okay? So we can produce dog whistles, which give signals to the dog for him to respond without disturbing anybody in the neighborhood, yeah? In general, the speed of sound is determined by the medium it's going through, and it depends on the elastic property of the medium and the inertial property. So it varies directly with the elastic property and inversely with the inertial property, okay? So the elasticity, the sound waves, the particles need to be able to move back and forth. That's your elasticity, yeah? And the resistance to motion is the inertia, resistance to change, yeah? So typically we have higher speeds of sound seen in solids, then lower in liquids, and lower still in gases. And this has something to do with the density of the material and the compressibility, yeah? So if we just get a feel for the numbers, you don't have to memorize any of this. This is the velocity of the wave, for sound wave, in meters per second, yeah? In gases, in air, about 331 meters per second at 0 degrees Celsius. You'll see that the speed also varies with the temperature. As the temperature rises, the particles can move more freely. Hence, we expect the velocity to go up, okay? We will come back to that later on. Let's look at some liquid, maybe fresh water, 1,480 meters per second. So huge jump there from gas to liquid. And let's look at a solid, maybe steel, 5,960 meters per second. So very much faster in solids, okay? Here's how the velocity changes with temperature. So we saw that it's 331 meters per second at 0 degrees Celsius. So we get 331 times the square root of the temperature divided by 273 Kelvin. Now we haven't studied the temperature scale yet, but the MKS units for temperature are Kelvin, and Kelvin is Celsius plus 273. So at 0 degrees, we have the temperature will be 273 Kelvin, 0 plus 273. Yeah? If you have 1 degree Celsius, it's going to be 274, and so on. So in this equation, when you input your temperature, make sure you convert this value T to Kelvin if it's not given to you in Kelvin, and this number will be 273. Okay? We'll do an example to make it more clear. Here's the example. Given that 331 meters per second is the speed of sound in air at 0 degrees Celsius, calculate the speed at room temperature, which is 22 Celsius. So Celsius and centigrade, I'm going to use interchangeably, okay? So one of the first things we have to do is to convert 22 Celsius to Kelvin. Let me get my Kelvin temperatures for both of them, actually. So the initial temperature at 0 degrees is going to be 0 plus 273 Kelvin, which is just the same as 273 Kelvin, right? We've done this before. And the temperature at which we want the speed is 22 degrees Celsius. Whenever we write Celsius, we're supposed to write degrees Celsius. So that's 22 plus 273. And since I mentioned that degree, when we write Kelvin, we don't write a degree. So it's just K, no degree before it. So this becomes 295 Kelvin. And now you just need to use the equation for velocity and substitute your values in. So it's going to become V equals 331 square root of 295, the temperature that we are at, compared to 0 degrees Celsius, 273. Okay? Square root of the whole thing. And you just work this out in your calculator. You should get the same result as me, which you're going to see on the next slide. Okay. So you will notice here that when I wrote in the values, I didn't write the meters per second. I didn't write the K. I feel that it causes more confusion to write these things in, because then you don't know if it's a variable or this is the unit. So long as you're in MKS units, you don't need to bother to write the units in here. Personally, I prefer that method. Okay. So you should get 344 meters per second. Since the temperature has increased, we expect the velocity to increase from 331 to 344 meters per second. So always check for reasonableness like that.